Hello, everyone. My name is Andrew Benton.
I am Stephen Georges.
My name is Rebecca Olusola.
I'm Brian McLean.
And we are the Dye-Sensitized Solar Cell Group from FAMU.
So our project goals for this summer included fabricating our own individual solar cells using organic plant dyes locally available to us. By doing this, we're able to measure the effectiveness and generate a characteristic curve for each of these devices. And by creating these curves, we're able to justify the effectiveness of each cell. So why dye-sensitized solar cells? Dye-sensitized solar cells allows us to use renewable energy and the natural materials locally available to us through a variety of fruits and vegetables to be able to develop a solar cell. We're able to easily fabricate these devices through the locally grown goods near us, and we're able to easily incorporate them into our daily lives. By doing this, we're also able to provide a visually pleasing view of the solar cells by using different dyes and shades to produce the solar cell. So where did dye-sensitized solar cells come from? It came from the process similar to plants. Plants are able to use photosynthesis to provide them a food source by using photons in sunlight. And similar to that, dye-sensitized solar cells are able to use the photons in sunlight and formulate a band gap. And that band gap is able to then formulate electricity that can be later on used to power a load. Dye-sensitized solar cells have similar properties to a diode or a semiconductor. And as you can see to the bottom right, we're able to see the characteristic curve of a diode and a solar cell. We're able to see the characteristics of the relationship between current and voltage, which formulates the IV curve, and the relationship between power and voltage, which is the power curve. Dye-sensitized solar cells are able to be formulated through a 5-step process, which includes the absorption of light, the photons, and by doing this into a sheet of titanium oxide, we're able to generate, there's a generation of excitons, which are electrons, the energy from electrons and holes being formulated. The diffusion of these excitons to an active interface, which is our dyes from our fruits and vegetables, we're able to then create a charge separation, which is known as a band gap in the P-type and N-type material. By doing this, charges are able to be transported through this band gap and later on collected similar to a capacitor or battery for later on use to power a load.
And so the methodology we chose for creating these cells is, first things first, we chose a variety of dyes. Some of them include limes, peaches, blueberries, and specifically a very powerful one that we had was raspberries. From there, we went about fabricating the cells. You can see a visual of that in the center. It's 2 glass slides, one of them with a thin sheet of titanium dioxide, which we covered the dye in. The other one, a backing with a sort of metallic plate. And then in between them, there is a electrolyte, which supplied the extra electrons. From there, we made a circuit with a potentiometer and multimeters to measure the voltage and the current at different levels of resistances. We can see an example of that on the bottom left. And then finally, we gathered the data from that, and we used that to plot the IV and the power curves.
So from the previous slide, you had a circuit schematic. This is what it looked like in our research we were doing at home. So to give you an orientation before you watch the short video, at the very top at 12 o'clock is a silicon photovoltaic solar cell. Down at the bottom, you have the 2 multimeters, voltmeter on the left and the ammeter on the right. My hands are on a potentiometer that's going to be used to change the resistance, and we did this sort of in a staircase step-down manner for each trial. And then right above the 2 meters in the center is an LED in series, and you should, as the resistance change, you should see the illumination of the LED get brighter.
And so here we have some of our IV curves from our results. As you can see, the raspberry curve was the most effective by far. On the right, you can see the values that we used to craft the specific graph. Down at the bottom left, we have the peach skin IV curve. That one was the second most effective. It shares a lot of chemical similarities with raspberries, specifically the existence of a chemical called anthocyanine. And then comparatively, the lemon and lime, which are both citric acids, they were much less effective, both for current generation and for power generation. And then we can see here the comparison between them purely. Raspberry at the very top, peach second, and then both lemon and lime relatively close in the bottom. However, whenever you compare the dye-sensitized cells we were able to make to a commercially available silicon cell, the one that Brian used in the demonstration, you can see that their total, both their IV curve and their total power output is just dwarfed by what's on the market right now. And so that's definitely one thing that dye-sensitized solar cells need to focus on in order to become a viable product in the future. Here we have some other charts showing some results from different cell types. We have on the left a dye-sensitized solar cell using BlackBerry specifically, and the changing of the angle that they viewed in the sun, showing that you need the maximum amount of area exposed to the light in order to get the most amount of power of it, and in this case it would be directly perpendicular to the source. And then on the right we have 2 cheap dollar store calculator silicon solar cells, and we show both their power and their voltage output is a lot stronger, as well as a lot more steady than what you see in the dye-sensitized solar cells that we tested. And so, again, an analysis of it, we saw that both raspberries and peach skins were way more effective, this being due to the anthocyanine that's located inside of them. And then lemons and limes were less so as citric acids. However, one thing that we weren't able to really show, it was that we tried both peach juice, cherry juice, and pomegranate juice, and all of them were just too unstable to get actual solid measurements of. We believe that this is due to the lack of anthocyanine inside of the juices compared to the skin, and this would be more resilient to oxidation, which we feel like is the reason why they were not stable enough to really measure. Again, however, the silicon cells in terms of power were just way more effective than the other cells, so there's still a long way to go before dye-sensitized solar cells are commercially viable.
I'm excited in bringing this material to my classroom in the coming school years. I see 4 possible areas for integration into just about any science class. We have an energy unit somewhere. It's hard to get away from energy. Having students engage with the idea of energy use, eventually focusing down on solar energy through a PowerPoint slideshow with a couple of dozen images, photographs, diagrams that they may or may not have seen, but pretty superficial in terms of they should be appealing and not intimidating. Then each student or pair of students would get one of the slides and work up a 2 to 4 minute oral presentation to their peers to be dropped in periodically throughout the rest of the unit or the semester. Hard to have a science class at some point where you're not talking about elements and electrons. And the idea of the photoelectric effect would be a good point of integration. The PhET simulation for the photoelectric effect from the University of Colorado at Boulder is very reliable and set up with several variables to be able to manipulate. And we will visit this sort of in a guided inquiry activity in which the students address it with a claim evidence reasoning lab. As you saw, we were pleasantly surprised with just how reliable the less than $10, so to speak, photovoltaic cells are, and that certainly lends itself well to public high school classroom use. And it's easy enough to set up the 2 multimeter system, and students should be able to generate and be able to compare solar panels just as a technician or installer for solar systems would do here in town. This would also be a point where students would actually use and not just do a quick dash at Excel for a simple table, but use the graphics and the graphing processes to be able to analyze their data and then to compare different panels. Lastly, hopefully in the spring, we'll be able to have some type of hands-on, more traditional chemistry laboratory activities in synthesizing the dye-sensitized solar cells. There are a couple of reliable commercial suppliers for schools that have kits available, and I probably will open this up a little bit more rather than everybody doing the same thing, is to have some groups address one particular variable of interest, whether it's the electrolyte solution, for example, changing from an iodine-based to a cobalt-based, to look at carbon sources going from pencil graphite to soot, and then looking at different plant tissues as source of dyes.
Throughout our research, we came across the following problems. Our first problem was that some of our glass slides were broke from our solar cell kit, and also the titanium dioxide was not thick enough for our solar cells to function correctly. So to combat this problem, we decided to limit our scope by removing our solar cells that did not work or were damaged. And we made the most of our working solar cells. And we also experimented with different types of solar cells, including a silicon-based solar cell. A second problem that we came across was our controlled environment. We could not perfectly control our temperature or our illumination. So to get past this problem, we decided to control our environment by using halogen lamps and indoor testing to control our temperature. Because in Florida, the temperature was going above 95 degrees, and solar cells do not function efficiently with 95-degree temperature. They function better, but 20 degrees below that temperature. And another problem we came across was a material shortage. We did not have access to potentiometers at first, and we also only had 1 multimeter. And we also had problems with our fresh source materials, including our fruits and vegetables. So to get around these problems, we decided to order the potentiometer and order the extra multimeter that we needed. Next slide, please. So for future improvements and further research, we believe that experimenting in the lab would be better for a more controlled environment. Another approach would be testing cells from the same plant but using different components. So this would allow, so instead of using just the pure juices from the fruits, we can also use the skins, because we ran into the problem of using pure juices that they were unstable, the measurements were unstable. But while with plant skins, we would have more stable measurements. Another approach would be mixing different types of plant dyes. So for example, that would be mixing raspberry juice with blackberry juice and experimenting with that solar cell to see if it creates a more efficient solar cell. And one more approach would be, further research would be to find ways to improve the efficiency and lifespan of solar cells, because currently solar cells does not have a long lifespan. So that can be improved upon with further research. Thank you.